It is long. That was question two. I just left. Parameters.
Oh, it was you.
Yeah, my bad.
Oh. Luke was like, my assigned on this.
Yeah, I know.
That seemed more logical to me.
Yeah. I mean, that's what I did too. I mean, I gave you kind of a full kind of beam equation for that one, just because that's how the equation is formulated.
Yeah.
When you have a bunch of constants, I was just otherwise just take on the problems. You can never.
I just left the derivative. You did everything.
Like I,
So.
Freaked me out, so I'm like, oh.
Okay.
And then I was like, horrible, kind of so I was just
Take derivatives and you show away.
I didn't like get it. So. Oh, like,
Separated out. It's easy stuff. Constant. Very low. So.
like, no. Oh, my mirror.
That's gonna be.
That's true. Yeah, it's good. It's good for the inequality constraints. You know me all too well. Yeah. But probably not till next week. But I want to finish linear program.
Did you use that for your
And I'll make sure the midterm problems are doable in the time. Just massive.
It's probably. It's like over, like 200 plus. I was when I was in high school, I'm like, my my fucking uncle
We're good. Kind of this forward a very busy site. Saw a lot of vendors and our first dance lesson and everything too. Monday, that's my whole life. But granted, my wife has waiting on generally the woman has a lot more right, but so she's working even harder, but still plenty of stuff, plenty of
for us.
Oh, really?
Yeah. My parents. Our background all the time. The male's parent.
Oh. So they have, then if they're paying, then they have say on how.
Yeah, so it'd be my, I'm see that. It's there.
It's your parents.
Yeah, it's like separate.
I'm not there. Right.
Gotcha. Yeah, my wife's parents are paying, they're not paying for everything, they're paying it. Invite all their friends. So my parents are helping out with too, so they're inviting.
A little too hardcore.
Make the money, bro.
One thing is.
Well, we're inviting 200 users, so we're expecting maybe like 210. All right, it's 5:30. Let's go and get started. All right, good evening, everybody. How's everyone doing today? Doing good. You smile, so that's generally a good thing. So that's not that common by week 6. Usually everyone is kind of sad and stressed at this point, but you guys are still going strong, so that's good. Okay, so the plan for today, so I originally planned to have the midterm project ready for you guys. As many things in life, life did not go as planned, and so I don't have it ready for you guys today. But Thursday we're going to talk about the midterm project. Okay. So instead today we're going to talk about more element types. And so on last Thursday we talked about, or last Tuesday, I guess, we talked about the 2D element types. And so today we're going to talk about the 3D element types. And so it's more or less kind of a repeat of what we talked about last Tuesday, except in the third dimension. So that's going to make things a little bit more complicated, but also kind of very interesting to see as well. Okay. All right, and so let me give you guys a little bit of heads up for how the next few weeks are going to go, because once the midterm project is out there, I know that's going to dominate everyone's kind of mind thinking. So of course, we have activity 3 that's due this Friday. I do have one more ANSYS activity that I want to do while you guys are working on the midterm project. Okay, it's the ANSYS activity 3. Actually, I think I gave you guys an extra weekend to work on. So that's due next Monday.
Cool. Second.
There's going to be ANSYS activity 2. Right, activity 4, excuse me. So activity 4, we're going to do that next Thursday, and then it's going to be due a week and a half after that as well. Next Thursday, that's going to be then it's going to be due the following Monday, so that would be not the 12th, 13th, 16th. Same kind of time frame as this current activity, so you have kind of looks like a week and a half to kind of do activity 4 for the midterm project. So we're going to introduce this project on Thursday. So Thursday is going to be the 28th of September. And then it's going to be due about a month later. So I usually have it due on Halloween or the day after Halloween. So let's say November 1st. I don't know what day of the week November 1st is going to be, but that's so Wednesday.
Yep.
Okay, so it's going to be due on a Wednesday, November 1st. Okay, that timing actually works out well, because then we have kind of one extra day, the Tuesday to kind of talk about it in class, and then we have the Wednesday office hours if you have any last minute questions. So Wednesday is a good due date for it. Okay, so that's what the timeline is going to look like for the next few weeks. And so we're going to introduce the project on Thursday, but there just kind of be aware that there is one more activity that you're kind of doing in that time frame. So and so make sure you kind of account for both kind of when you're setting time aside to work on portion stuff. Okay. Any questions about any of this? Yes.
Is the midterm project open-ended?
No. So the midterm project, I'm going to give you kind of similar to the activities, and so I'm going to give you a CAD file to work on, and so I'm going to give you a choice of 3. And then you can kind of choose one of the three to work on. And then basically you're gonna be doing the finite element, all the finite element stuff on your own. So you're gonna be choosing the meshing, the boundary conditions. You're gonna choose several different configurations for the boundary conditions. And then you're gonna, more importantly, you're gonna write up the report. So it's gonna be kind of like a miniature, it's like a miniature version of your final project. And the final project is the one that's open. So you can choose kind of your topics. The midterm project, I want to kind of contain it just because, you know, we're still kind of learning ANSYS. Yes.
But that project. It's gonna be like a take home and then we submit it on a due date.
Exactly, yeah, yeah, so I don't have any planned time in class to work on the project, and so it's gonna be kind of all on your own time, but that's why I kind of give you a little bit over a month. Yeah, the FEA part of the midterm project should be fairly quick, and so it's not too different than what we've been doing in the activities, it's more the writing of the report. That'll be the first time I'm really asking you to kind of formalize, you know, describing your methodology and kind of describing your results, analyzing your results, and so that's the part that's going to be new. All right, any other questions on this? Okay, all right, so let's go ahead and get started with the lecture today. And so the lecture today, we're going over 3D element types. All right. So kind of continuing right along where we left off last Tuesday. And so, you know, we're still kind of in this mode of talking about elements, okay? Except today we're moving on to 3D. And so today's lecture is probably gonna be a lot more relevant to most of the things we do in this class. Because, you know, even though the 2D is kind of useful for introducing these concepts, you know, 3D is the one we actually use because we live in a three-dimensional world. But a lot of the trends and a lot of the concepts that we talked about last week are still going to apply here as well. Okay. And so just like in 2D, you know, there are two main categories of elements, both in terms of its shape and in terms of its origin. Okay. So for the shape, kind of very similar to our 2D elements, we have kind of two options here. We have the triangular elements and the kind of the rectangular elements. Okay. So in 3D, the triangular element types are called the tetrahedrons or the tetrahedrals. And then the rectangular element types are called the hexahedrons. And so tetrahedrons are just a four-sided pyramid, and so they look something like this. So that dotted line in the back basically tells you that the two corners on the sides are connected by a single edge. Okay. I think when most people draw pyramids, they draw a pyramid with a square base, but think of this as a pyramid with the triangular base. Okay. And the hexahedrons are just a fancy name for just a box. And so the hex part of hexahedrons it stands for 6, okay? Just like a hexagon, but a hexahedron is a 6-sided polygon, so which is just a box or a brick. So you'll hear me kind of interchange, and so sometimes I call them hexahedrons or hexahedrals. tetrahedrons or tetrahedrals are all the same. Okay? Technically, tetrahedron and hexahedron is those are the nouns, and tetrahedral and hexahedral are adjectives. So, but they're all the same for this. And of course, the two options we have for the order are either linear, quadratic. And remember, so on Tuesday, we kind of talked a bit more about kind of what this means. And so linear and quadratic here refers to the order of the shape function for the element. And just like we talked about last Tuesday, the shape functions are used for a variety of different. So they're kind of our first approximating polynomial for when we're kind of approximating our solution to our ODEs. They're used to kind of take derivatives for certain things. And whether your order is either linear or quadratic has a lot of effect on your solution. And so when we ended on Tuesday, we talked about this concept of shear walking, which only really occurs for linear and polynomials. All right. And so what we're going to do today is we're going to take kind of a very brief tour of all the different element types. So we'll talk about the linear tet, the quadratic tet, the linear hex, and the quadratic hex, and we'll look and see what their shape functions look like. And then we'll kind of talk more about kind of more practical considerations that you consider when you're meshing your geometry in ANSYS or just any kind of problem. All right. Any questions on this? Okay, all right, so let's go ahead and start our tour. Let's start with the linear tetrahedron. The linear tetrahedron looks kind of exactly as what we drew kind of there. Four-sided pyramid. And just like we did for the 2D elements, the kind of the key feature here is going to be the number of vertices or the number of nodes that we have. And so we have 4 nodes here. So node 1, 2, 3, 4. So that means our shape function here is going to have 4 terms. And so let's kind of write out kind of the generic form for the shape function. But remember, let's keep in mind that we're in 3D now, right? Not only do we need to include X and Y in our shape function, we also need to include Z as well. You have X, Y, Z. All right, so as always, we're going to start with the constant term. So we're going to start with C0. Okay. So C0 is just a constant, so it's not multiplied by any variable, not X, Y, or Z. We have C1X, Y, C3, Z. Okay. So what we have here is the simplest shape function that you can possibly have in 3 dimensions. And so you can see here that we have a constant term, and then we have a term that accounts for each direction. So we have an X term, a Y term, and a Z term. Because the basic requirements that we have for the shape function is that we have to be able to account for changes in all 3 directions. Okay. So you can't really get simpler than this, because if we eliminate one term from this, let's say we eliminate the y term, then our solution, our finite element solution, wouldn't be able to capture any changes in the y direction. Very big weakness. So this is basically kind of as simple as you can get, while still getting a feasible, useful finite element solution. Okay, so this is kind of the simplest element. It has a lot of uses. So actually, I think I may have talked about this on Tuesday, but a lot of the work that I've done in my own research, especially in CFD, I use linear tests a lot, and so I talk about it here as if it's kind of the simplest one, but it's still kind of it forms the foundation for a lot of really complex FEA. So I would say it's still very, very useful. Okay. You just kind of have to know how to use it. And its most useful property that we talked about on Tuesday, so it shares this with kind of the triangular elements of 2D, is what's called its simplex property, which means that you can use it to fill basically almost any space in 3 dimensions. Which means that it's always going to be reliable for meshing. So no matter how complicated your geometry is, no matter how weird it is, how many twists and turns it has, how fine the details are, tetrahedrons are going to be there for you. Tetrahedrons, they always have your back. So as long as you kind of give it a relatively small element size, the tetrahedrons are always going to be reliable for getting you a mesh. Okay, and as you start to do FEA and kind of more and more complicated geometries, you're going to start to appreciate this property a lot more, because one error, and a lot of you will experience this when you do your final project. One error that you'll find a lot is that ANSYS is going to fail in meshing. It's going to say that it's not able to produce a mesh, and you're going to be pulling your hair out, kind of like why isn't this working? And then when you're going to come back to the tetrahedrons, and it's going to be there, okay, like your best friend. Okay. But that's not to say that the linear tests don't have its issues, and so in particular, the linear tetrahedrons are susceptible to shear locking. Shear locking was this kind of phenomenon where if you use a linear triangular element in a structural simulation, then the structure can sometimes kind of lock up if you're not too careful, which results in kind of very low, or at least perceived to be very low deformations. And so if you're going to use linear tetrahedrons for a structural problem, the only way that it kind of works is if you make the element size very, very small, okay, which can drive up your cost. And so it's not the best for every situation, but it always kind of gives you a good start. All right, any questions on the linear tetrahedron? Yes.
Is there any similar to shear locking for like heat transfer analysis on ANSYS?
Yeah, no, it's a good question. So heat transfer and fluids actually don't have the same problems for shear locking, and that's mostly due to the kind of the structure of the governor. So shear locking is kind of a combination of kind of the linear tech and also just the structural, just the kind of the characteristics of the structural equation make it so that happens. So for the heat equation, for heat transfer, you know, you do have kind of second order derivatives there, which would kind of drive this. But just the way that it's formulated is that it's kind of just as a very simple kind of a Laplace term in the heat equation, that it just doesn't happen. So it's a much more well-behaved equation than the structural equation. Actually, you know, for a lot of the work, you know, for all the CFD work, you know, fluids is kind of the same way. So fluids, Navier-Stokes behaves very similarly to the heat equation. So that's why you see a lot of CFD codes actually use linear tests, because it's just not as much of an issue. All right, any other questions on the linear test? Okay, so let's move on to the quadratic tetrahedral. Okay. And so for the quadratic tetrahedron, you know, just like we did in the 2D case, we're going to increase the order of our shape functions. And so what that's going to require is that it's going to require we add some additional nodes to our element. Go ahead and draw the element one more time. And so, of course, we start with our corner nodes. We have nodes 1, 2, 3, and 4. So that's the same as our linear tetrahedron. Okay? But just like we did in 2D, we're going to add some additional nodes in the middles of the edges. Okay. And so in between each node, we're going to add some additional ones. So we're going to add 1, 2, 3, 4, 5, 6 more nodes. Okay. 5, 6, 7, 8, 9, 10. So we have 10 total nodes. And so what that means is that our shape function can have up to 10 terms. Okay. Okay, so let's write out kind of what the shape function looks like, at least the function. Okay, so we start with our constant term and our linear term. So this is the same as before, C0 plus C1x plus C2y plus C3. From here, we can add the quadratic terms. And so, you know, I'm going to add up kind of the singular terms first. Okay. C4x squared plus C5y squared plus C6 squared. So that's 7 terms. We can add 3 more. So let's go ahead and add the cross terms. And so we have plus C7xy plus 8 plus C9 . All right, and so just based on the number of terms from the shape function, we can see this is a big improvement over the linear tetrahedron. Okay, of course, that improvement comes with increased cost, but you know, a lot of times that cost is worth it. Okay. All right, so just some features for the quadratic tetrahedron. So just like we saw in the 2D case, on a per element basis, the quadratic tet is going to be more expensive. So the amount of computational power it takes to compute a solution for one quadratic tetrahedron is greater than the linear. Okay, you can just kind of see that just directly in the shape function, just the number of terms. But of course, that extra cost doesn't go to nothing, and so, quadratic tetrahedron in general will give you better accuracy. Okay. And that better accuracy kind of goes in kind of multiple directions. So it's not a, accuracy, there's a lot of things that can kind of contribute to accuracy. But the fact that we have quadratic terms here, and when we take derivatives, you get kind of non-constants here is a very, very big deal. And so, the increased accuracy that you get from a quadratic tetrahedron can either be sometimes just, kind of very small, but it can sometimes make a very, very big difference. Especially with shear locking. So when you have a quadratic tetrahedron, you basically don't have to worry about shear locking at all. So that's kind of just one less kind of headache to kind of. The good thing though, at least with the quadratic tetrahedron, is that we still kind of maintain the same simplex property as before, because the simplex property is a property of the shape, not necessarily the order. Meaning that, remember that, and the simplex property means that you can use it to mesh almost any geometry. So just like I said in 2D finite elements, when you're working with kind of a commercial software like ANSYS, and ANSYS kind of gives you the option to use a quadratic element like this, there's not really that much reason to use a linear finite element. Okay. The only reason you would use a linear finite element is that, I can tell you from experience that trying to implement a quadratic finite element like this in code is a huge pain. It's like exponentially more complicated than the linear one. But the good thing is that when you're using ANSYS, that's what you kind of pay ANSYS to do. You pay ANSYS to do the programming, so you can just kind of enjoy the software. So, when you're using ANSYS, I would say almost always you should use kind of a quadratic element, just because it's just so easy for you to do. But just know that there was a lot of work that kind of went into this. And a question I get asked every year is that, is it possible to have cubic elements? And so can you have, finite elements that have a cubic shape function? And of course, absolutely, you can have a cubic finite element. Just don't ask me to do the programming for that, because that is a nightmare. I know there are some kind of research softwares that kind of go into that realm, mostly for kind of very niche kind of situations. We have a very high order differential equation. So I know electromagnetism kind of gets into that area. So like we talk about Maxwell's equations and things like that, but it's not that common. So that's why for ANSYS, they place the limit at quadratic, just because quadratic kind of is the highest you kind of want to go for most kind of mechanics. All right, any questions on the quadratic tetrahedron? Okay, let's go over the linear hexes. All right, so let's look at the linear hexahedron. Okay. So just like the linear tet, we're going to have a corner. We're going to have a node at every corner. So we're going to have 8 nodes in total. So let's go ahead and write out the shape function for this. So the shape function is gonna have 8 terms. Starting z 0 plus x plus y plus c3z. Okay. So that's our constant term and our pure linear terms. And so, hopefully you notice kind of right away just how much of an improvement the linear hex is, because, if you look at the linear text, the linear tetrahedron only had 4 nodes. So our shape function also only had 4 terms. Okay. And so for the hexahedron, we still are looking at a linear element here, but we have twice as many terms to work with. So, on a per element basis, it's just that much better than the linear tetrahedron. Okay. And so the 4 remaining terms here are going to be our pseudo linear terms. So they're technically not linear because they have multiple variables multiplied by each other, but they're pseudo linear because each term only has a linear order. Okay, we're gonna have C4 xy plus C5 z, C6 yz. Right, so those are all the first order cross terms, and so we have x times y, x times z, and then y times z. Okay, but we have one more term here, and we can't go to quadratic because if we did, then this would be a quadratic element. So our last term here is going to be x y z. So it's 7x. Twice as many terms as the linear tetrahedron. So, twice as this. Okay. So just like its 2D counterparts, if you have the ability to use hexahedrons, that's generally going to lead to a more superior solution. And that reason is because the shape function has more terms. What you'll and so if you kind of dive more deeper into it, the hexahedrons can kind of resist skewing a bit better. Okay. And so if you have a skewed hexahedron, that's usually not as bad as if you have a skewed tetrahedron. Okay. But the problem is that it's usually a lot more difficult to mesh a geometry using hexahedrons. And it's especially challenging when you have geometries that have a lot of curved surfaces. Right, so if you think back to activity 3, actually quite a lot of you were actually successful in getting a hexahedron mesh on the post. Which is good because the post has a curved surface. But I think what probably a lot of you notice is that if as long as you make the elements kind of small enough, it makes it easier to get a hexahedron mesh on something. But that's not always going to be true. So I would say that if you could swing it, if you can do it, use the hexes, but if not, using the text is perfect. All right, any questions on the linear hexahedron? Okay, all right, and then finally, let's talk about the quadratic hexahedron. Let me go ahead and draw the quadratic hex here. So just like our linear hex, we have all of our corner nodes here. But just the corner nodes alone are not enough to give us all the quadratic terms. And so we're going to add nodes in the middles of all the edges. A bunch of mid. Right. So if you were counting the nodes as I was writing it, or maybe you were counting the nodes as you're drawing yourself, what you'll see is that there's 20 nodes. Okay, so it's a lot. We were 8 corner nodes, and then for each edge of the box, we have 12 edges on a box. We're going to add additional nodes. We have 9, 10, 12. I usually miss one when I look. 20. Good. Getting better at counting every semester. Okay, and so of course we can make our shape function from here. But this is going to take a little bit of time because we have 20 terms that we have to write. Okay, so let's go ahead and start. So we have our constant term, so that's always going to be there. C0, C1x, C2y, C3c. Okay. Then we have all of our cross terms, and so we have C4, xy, plus C5, C plus C6. Then we have our triple cross term, and so this is our for our linear x. This was 7 xy. So those first 8 terms right there come from the linear x, but then we can add an additional 12 terms here because of the additional nodes that we. Let's jump into the quadratic terms. So we have C8 x squared plus 9 y squared 10 c squared. Okay. Next, we have our quadratic cross term. So this is going to be C11 y plus C12 plus C13 squared x plus C14 y squared z plus C15 d squared x plus 16 d squared y. Okay. So there's 6 of those terms, and so it's x. It's some variable squared multiplied by another variable linear power. Okay. We have 3 more terms to go. And so, you know, you in reality, you know, you have a little bit of choice here in terms of you know, how to form these last 3 terms. But but kind of the standard here is to use kind of our triple cross here. And so we're going to use x, y, z. So all 3 terms here are going to show up, but we're going to make each variable here is going to take a turn becoming quadratic. Take C17 x squared y z plus C18 x y squared z plus C19 x y z. Yeah, but it's not me. I tried. It's yeah, it's not fun. It's my old lab mate would always have this saying was that he would say the juice is not worth the squeeze. And so you know, this would take a very hard squeeze to get any kind of juice from. And it's debatable whether someone else is doing the programming, yeah, absolutely it's worth the squeeze, but not when it's I'm just rambling at this point. I'm sorry, I'm really hungry right now. Okay. Okay, so you can tell just from the shape function here that this is a very expensive element, and so on a per element basis, this is as expensive as it gets. But this also means that it's the most accurate element on a per element basis. And kind of the benefit of having all these terms is that you can capture lots of different types of solution behavior. So, you know, no matter how complex your stress distribution may be, maybe you're having stress that kind of rapidly changes in a short period of time, which is very common in structural finite elements. This element will likely be able to capture. And so just like its kind of linear cousin, you know, quadratic hexahedron also has the same kind of limitations in terms of meshing. Okay, and so if you have kind of a lot of kind of curved features to your geometry, you have kind of lots of small features. You know, a lot of times the quadratic hexahedron will kind of struggle to mesh those. Okay. But if you can get it to work, then it's okay. And actually, you know, a lot of times people kind of do kind of a cost analysis benefit in their head. And so, because quadratic hexahedrons are kind of so valuable and so good if you can get them to mesh, a lot of times people will actually modify their geometry in order to get it to work with the quadratic. Okay. And so what that usually means is that in particular, the thing that makes meshing really difficult in general, even for tetrahedrons, is when you have kind of lots and lots of small details in your model. Okay. And some examples of small geometrical details would be maybe you made a CAD model with threading. Okay. And so maybe you have some screw holes in your geometry, which is designed for a screw to go into. But those threads that you have in that screw hole are very, very tiny features. Some other kind of small features that may be there, maybe something kind of like small kind of some small decorative details on kind of the exterior of your geometry. And so there's kind of a lot of examples. And so when you have these kind of small features, usually what a lot of people do is they'll do something called defeaturing to kind of get rid of these small features, just to give your mesher a better chance to produce a good quality. So ANSYS does some defeaturing by default, and so it's actually one of the settings that you can specify for your mesh. And so if you look back at kind of your ANSYS project, if you're still working in activity 3, you can check it out as well. And so if you click on mesh and you click on and you go to kind of the bottom left hand corner of the screen for the details, you should see kind of a feature for defeaturing. And so if in case you're wondering what that is, by default ANSYS will try to ignore any kind of very, very, very tiny. And that's basically just to give the mesher a helping hand. But even despite that, it's a lot of times when people run FEA, they'll do kind of manual defeaturing, or they'll actually go into their SolidWorks part and try to eliminate as many of these kind of small features as possible, just to kind of make it kind of easier to mesh. Okay. And so that's going to give you a better chance at making it work with quadratic hexes or linear hexes. It even helps you with your linear tetrahedrons as well, because what can happen sometimes is that if you have lots of tiny features, and so let's say that we have kind of a very large structure here. We'll pretend that your structure is shaped like a potato for some weird reason. Okay. You have kind of screw holes maybe here on one side of the structure, okay? And if these screw holes are threaded, and so we have threads in the screw holes there, and you probably have it in your original CAD geometry, just to kind of make sure that that you put threads in there when you go to manufacture or machine it. Okay. What's going to happen is that if you try to mesh this, even with tetrahedrons, in this area right here, you're going to get a very, very large concentration of elements, even if you specify large edge sites. And the reason for this is that when you specify an edge size for your mesh, that's the maximum edge size that the mesh can use. Okay? You don't really specify a minimum, because a lot of times, the mesher, what it has to do is that it kind of has to make your elements smaller, or it might have to distort the elements to kind of squeeze it into, all these kind of weird parts in your geometry. And so when you have kind of threads, or you have these kind of very, very tiny features, what happens is that ANSYS will try to make the elements in that area just really, really small, try to capture those features as kind of faithfully as possible. Because that's one of the objectives that the mesher will try to do, is that, you know, you have a geometry to a mesher, right? And basically what the mesher is going to do is that it's going to just kind of break apart your geometry and then almost basically kind of reconstruct it with elements. Right? And so one of the objectives of the mesher is to always try to represent the geometry as faithfully as it can. And so when you give the mesher kind of an object with a lot of kind of tiny features, then it's going to try to recreate all of this. And so that creates kind of a lot of tiny elements in that area. And ultimately what that's going to do is that it's going to drive your element count way up. So that's kind of, you know, not usually not a good thing. And so because what's going to, and so you can kind of visually see it too. And so if you were to mesh kind of a geometry like this, you'll see kind of lots and lots of tiny elements in this area. Whereas over here, you know, maybe you have kind of much bigger elements. And so it kind of creates kind of an imbalance of elements. Maybe you want to put more mesh density over here, but you're limited because, you know, around the small features you have, mesh has to be really tight. Okay. And so to kind of alleviate this, you know, one thing that you can do is you can either kind of manually defeature these, and so you can kind of get rid of the threads in that area, or you can kind of increase the tolerance on the automatic defeature. But that's one thing to kind of be aware of, you know. I'm not going to give you anything like that for the midterm project, but for the final project, you know, I think a lot of you will probably kind of struggle. You know, as you kind of try to mesh your geometries. Okay. All right. Any questions on defeaturing and kind of small mesh? Okay. All right, and so let me just go ahead and summarize kind of everything that we talked about in terms of elements, and then kind of give you a little bit of a choice or a flow chart in terms of how to choose the best element. All right, and so just to kind of summarize, you know, whether you're in 2D or 3D, you know, you have to make kind of two decisions on your mesh, or at least in terms of the types of elements. So you have to choose the shape of the element and the order. All right, so one of these decisions is quite easy, and so for the order, you know, like I mentioned, you know, it's unless you have a very good reason to do so, you know, maybe you're running kind of heat transfer simulations or CFD simulations, and maybe you want to cut down the cost as much as possible. Then, you know, you may consider doing linear elements, but if you're doing structural simulations, you know, almost always you're going to take quadratic. And in fact, I think if you don't specify anything, then by default, if you're running kind of any kind of structural simulation, whether it be static structure or maybe you're running a dynamic simulation, I think ANSYS will by default kind of choose a quadratic. And then the other decision that's a bit more interesting is you can either choose a triangular element, which is a tetrahedron or a triangle, or a rectangular element, which is a hexahedron or a quadrilateral. And they both kind of have pros and cons in terms of what they offer you for your. Okay, so let's go over the triangular elements first. And so for the triangular elements, basically the big benefit of using triangular elements is that they're able to mesh almost any geometry without fail. Still have to give an appropriate size for the elements, but for most cases, if you specify tetrahedron elements, you're going to be able to mesh it very, very reliably. Okay, and the main reason for this is because all the triangular elements have a simplest form. All right. The downside to this is that even though it can mesh any geometry, it may not be efficient in doing so. Okay. There are any questions? Good. And so what I mean by that is that when I say the triangular elements are not that efficient at filling space, it takes a lot of elements to kind of fill that space. Okay. And so, it may be able to mesh any geometry, but it may drive your cost up because it takes just a lot of elements and a lot of nodes to kind of fill space when compared to rectangular elements. All right. And so if you have a challenging geometry or you have a geometry that you're kind of struggling to mesh, consider going to the triangular elements. So that goes all right. And so on the other hand, rectangular elements, they're kind of the opposite of the triangles in this case, in that they sometimes struggle to mesh certain geometries. And so what I mean by that is that if you try to apply a hexahedral mesh to certain geometry, sometimes the mesh is just going to just flat out fail, and it's just isn't going to tell you that it can't do this. Or it's going to give you some error message that's so cryptic that it's impossible to know what's going on. Okay. But for the cases where it does work, it fills the geometry or it fills the space very efficiently. So it takes a lot less elements to fill a certain area of space compared to its triangular Not only that, and so not only does it take less elements to fill a space, is that on a per element basis, that you're getting more high quality solution. So per element, your accuracy is going to be much. And then the final benefit to using rectangular elements is that they don't get as skewed as the triangle. So just visually and kind of see your mesh just looks kind of nicer, and you have a better fate that you're not going to have kind of weird numerical issues that could show up. And so the elements are kind of less likely to get distorted. And so one other thing that I'll mention too is that, now that we kind of understand kind of the differences between the triangular and the rectangular elements, you're not limited to just a single element shape for your entire geometry. And so we saw this in activity 3, right? And so there are certain parts of the geometry where you can use one type of element, and you can use a different type of element on a different part of the geometry that may make more sense. And so that, of course, includes the element shape and the element order, but you can also apply different mesh sizing to different parts of the geometry as well. Actually, for more complicated geometries, that's generally what you're going to do. Is you're going to apply take each part of the geometry individually, take each part in your assembly, and then apply different meshing settings there to kind of achieve the mesh that you want, maximize the accuracy and minimize it. Remember, ultimately, that's what you want to do for your mesh. Try to get the most accurate solution possible, but spend the least amount of computational power. So that should kind of always be your mindset when you're meshing. So when you choose kind of what element to use, what sizing of element to use, kind of always have that idea in your head so that I want the most accurate solution, and I want to pay the least amount. Just like grocery shopping, right? So you want to get the highest quality ingredients for the lowest price possible. Not like I'm advertising smart. Okay, any questions on this? Yes.
So when you use like the automatic one where you don't specify like the shape or anything, and it sometimes does hexahedrons and sometimes like what is the method that ANSYS is using to determine, like, is it just saying like, oh, if I can't do hex, then try like a tetrahedron in this area, or does
Basically, yeah.
Oh.
And so it uses other heuristics, I know. So what it also does, I know, is that it looks at kind of the local curvature of the geometry in that area, and it kind of makes a decision based on that. And so if the local curvature is kind of a certain threshold, then it's just going to default to tetrahedron. If not, then it's going to give hexahedrons. So and so same thing for like kind of the size of the features. And so kind of sense it that the features in that circuit are small, and it's going to default as tetrahedron. And so it does do a little bit of trial and error, but then it also uses But those heuristics usually aren't the smartest, and so usually, as you kind of get better at ANSYS, you start to get kind of better. Kind of, you know your geometry a little better. Any other questions on this? All right, so we'll go ahead and end a little bit early today. So I left a little bit of time today to talk about the project, but the project's not ready, so I'll just let you guys go 10 minutes early. So thank you guys for coming today. On Thursday, we'll talk about the project and we'll talk about kind of the next activity. And we'll go from there. Thank you guys for coming today. I hope you guys have a good rest of your meeting, and I will see you guys on Thursday.
Oh, wait for.
You're like go all the way out.
Oh, that's why, yeah, I mean, I have an offer, and I'll
Say, okay, and then when you say, oh, I. Okay.
I'll do mine. Oh, yeah, thanks. But I thanks for on it. I never had
Yeah.
Oh, my friend background enchiladas. Yeah, okay.
I think that's one.
Enchiladas. Any final questions? Everything that's to be positive. Things like.